without stating so, present a version of the Nyquist that is only valid for open loop stable systems. But other chemi books have the full version. Most have the full version. Yeah, I mean, at least it should be staying the critical assumption for the limited version of Nyquist that they present. All right, now, remember that, so in frequency response, critical is what happens when I put S equals I omega. That's what we are plotting. We are plotting log of the magnitude of G of I omega and argument of G of I omega. So G of I omega is a complex number. And any complex number can be rewritten as the real part plus I times the imaginary part. But can also be rewritten as the magnitude of the complex number times e to the I argument of the complex number. Clear? And very important for what I'm going to talk in the first half of the class today. That the product of the transfer function, the same way if you have multiple, can be rewritten, of course, writing each one in polar form as magnitude multiplying two of those things, okay? The magnitude is multiplied, and the product of the exponentials is the exponential of the sums.
This is simulation for Nyquist.
No. This just put everything in context. I'm discussing something I'll bring, if I have time. We'll see how much time I'll have. I'll bring an example of what I'm going to be talking about. But this is something important to know. Yes?
What do you mean by it applies always?
Apply what?
Applies always.
This has, requires open loop stability, has this, it has no constraints. It always applies.
So why do we bother with the others?
Because a lot of the things that are done reported plot. For example, gain margin and phase margin, even though you can do equivalent with the Nyquist plot, it's not so easy to see, and it's not so intuitive. But yeah, that, and everybody, you wouldn't be educated properly in this class if you didn't know what the body plot was. If I just went through the Nyquist. All right. So what does that mean? That means that the magnitude of the product of two transfer functions is equal to the product of the magnitudes and the argument of the product is the sum of the arguments of the individual. Okay? Clear, everyone? All this is review, guys. Come on.
You sum the 200?
Because the product e to the a, what do we have? I have e to I argument g1, that's e to the I argument g2 if I multiply them two, right? But e to the a times e to the b is e to the a plus b.
So why are you not adding the one at the bottom?
Oh, oops. Because the plot was written in invisible chalk.
That's why.
Okay, sorry for how I didn't understand your question. That's why. All right. Now, let me make sure that I answer the question before I tackle some example problems from other times. Anything that has to do body stability criteria involves always body plot of GUGC of the product of everything in the loop. So, we have learned, if you're checking stability, so, checking stability, what do? You do body plot of GOL equals GUGC. If you do gain margin or phase margin, body plot of GOL. Okay? Anything has to do with stability of the closed loop system is body plot. However, there are two cases where we can avoid iterations if we do something smart. But so before that, let me remind you something. So one controller tuning method was the Ziegler-Nichols tuning method, which relies on the ultimate gain making.
So when you said body plot of GOL equals GUGC and body plot of GOL, aren't they the same thing?
I'm making the point that for most anything stability, you have to do body plot of GOL. Okay? Stability, gain margin, phase margin, you have to do body plot of GOL. However, we learned the Ziegler-Nichols tuning method. And the tuning method of Ziegler-Nichols relies which is, what is KU? KU is value of P control KC that causes magnitude of GOL I omega C naught exactly equal to virtual instability. Remember that? And PU is 2 pi over omega C naught. So far so good. Everything is review. I've been doing 35 minutes of review. Okay? Using directly the body stability criteria, what must we do? How do we find KU? So GOL is what in this case? GOL, which is GUGC. GC is what if we have just proportional control? KC. So that's GU KC. So what I would have to do, pick values of KC and iterate until you hit magnitude of GOL and I omega C naught equal approximately. And that's how you can find K. Okay? And also omega C. That would be a direct application of the body stability criteria. since I don't know what KU is, I would have to pick different values of KC, do body plots every time of GU KC. Okay?
Do we need a computer today?
Please, Juan, ask questions that have to do with understanding. I'm not going to answer that. Let's continue. So, before my train was there. What did we learn instead? Here's a key thing. We found a way we could do that without iterating. And that relied on a key thing. That positive reals have zero argument. Any positive real is the imaginary part, is the real part. Any number that is a positive real has angle 0, okay? Has 0 argument. As a result, if GOL can be rewritten as, let's say, GOL prime times any positive number. So let's say times, what's the name of the positive number? Okay. I haven't used P. So lowercase p, where p is a positive real number. P for positive. Okay? What we know, I'm referring here. So GOL is written as whatever it is times a positive real number. What will we have from there? We'll have the magnitude of GOL at I omega is going to be magnitude of GOL prime at I omega times magnitude of P. Okay? And what's magnitude of P? It's going to be P itself. So that's going to be GOL prime at I omega times P. But the more important point is argument of GOL, I omega, is going to be argument of GOL prime at I omega plus argument of P. I'm writing GOL as the product of divide GOL by a positive number, GOL prime times a positive real number. And the whole point is that the magnitude is the magnitude of GOL times the product, times the positive number, sorry. And the argument of GOL prime is the sum of the arguments of C. But what's the argument of the positive number? 0. With me? So, that means what? That the phase-lag plot, there shall be no double line, something like that. This is a double line of parentheses. That means what? That phi plot of GOL is equal to phi plot of GOL. No matter what. If I rewrite my GOL as a positive number times whatever is left, so if I know all of GOL except test for a positive number, I can avoid iterations for finding omega C naught. How would I find omega C naught? With the iterative method. I would pick a KC, right? And for each KC, I would have a different omega C naught, right? I will have a different frequency or phase, like it's minus 180. Okay? But here, if I do that, I can find omega C naught by finding the omega C naught of GOL prime. So, since they have the same phi plot, they have the same omega C. Are we okay? Clear now? That's the key point I wanted to first of all explain today. So, what did we do in Ziegler-Nichols? Oh, okay, actually, let me say another thing. And what about amplitude ratio at omega C naught? It's going to be what? It's going to be equal to the magnitude of GOL prime at I omega C naught, which I have from a body plot of GOL prime times P. So, if I have a specific value for magnitude of GOL for AR at omega C naught, okay, if I have a specific value for that, body plot of GOL prime will give me this part, I can find P. Then P is simply the AR at omega C naught over the magnitude of GOL prime at I omega C. That's a key point I want to explain. All right? So, let's go back to the Ziegler-Nichols scheme. And then we'll go to the family of problems that I'm looking at the time. I won't have the time to do them here. You'll see a lot of them in all the exams. I'll work at least one of them during the review session. I'm explaining the theory behind it now, and instead of doing numerical example, just show you how you do it, and numerical example will be at the review session. Clear, everyone?
On the last line, it says, so if what half is the, I don't know.
So if I have I, okay, so an example of what I just said is the Ziegler-Nichols tuning. Okay? So, we need to find Kc and omega C naught that give